Math 2414, Parametric Curves, Video 7, using Desmos to graph parametric curves. I forgot to take out these instructions here. They were left over from the previous video. But so far, we've seen quite a few sets of parametric equations. And for most of them, we sketched curves. The only one we haven't sketched a curve for is this guy in the middle right here. But we'll take a look at him in a moment. And on all of these, we did eliminate the parameter. So I'm just going to remind you what those rectangular equations were. In fact, to kind of get you used to the lingo that we're going to be using if you take Calculus 3, these across the top are called parametric equations for the obvious reasons. But each one of them has an equivalent rectangular equation. From this point forward in your future math classes, if you ever hear the adjective rectangular and you're not talking about geometry, it almost always means you're talking about x's and y's only. And in this case, eliminating the parameter is what gave us our rectangular equations. So what were our rectangular equations? Well, this one, the first one was x squared plus y squared equals 1. The second one was x equals y squared minus 3y, I think it was. Hold on, almost, hold on. It was y squared minus 4y plus 3. The one in the middle was y equals 1 over t, excuse me, or 1 over x, and I just realized that is not the parametric equations we had before. It was tangent and cotangent. But a good exercise is to ask yourself, what would you do if it was tangent and secant? What trig identity would you use to connect the two? When we eliminated the parameter in the x equals t squared minus 1 and y equals t to the fourth minus 1, I know we ended up with y equals x plus 1 squared minus 1, and that was y equals x squared plus 2x. And then for the last one, we just ended up with y equals x squared. But sometimes graphing these or even eliminating the parameter is difficult by hand. And in the case of eliminating the parameter, sometimes it's actually impossible. So it's nice to have some technology at our disposal. So I'm going to show you how to use Desmos, desmos.com, to graph parametric equations. Now, some of you are already familiar with Desmos, but if not, let me take you there. You would just go to desmos.com and then click Graphing Calculator. You can create an account if you want. It's not necessary. I've got a lot of graphs saved, but let's not worry about those right now. So how do you graph parametric equations in Desmos? The first thing you want to do, well, you don't have to, but I'm going to do it for convenience, is define the functions that give you the x and the y, but you want to define them in regular function notation. For example, if we wanted to do, let's do the one we did last, x equals sine of t and y equals sine squared of t. If I wanted to do that, then I would start by defining two functions, f of x equals sine of x, and g of x equals sine squared of x. And if you notice, it's graphing both of them. There's the graph of sine x. There's the graph of cosine x, of sine squared x. Let's do this to make them a little bit chunkier. And you might be thinking, but didn't it say sine of t and sine squared of t? And you would be correct, but all we're doing is defining functions here, and the variable that you use is irrelevant. At least I think it is. I think I can use a different variable like y. Let's see if it'll recognize that. Oh, look at that. What if I use t? Okay, just learned something. It's not going to get upset if I do that, I think. We're about to find out. To graph the parametric equation, you type an ordered pair using your parametric functions. Okay, it's going to let it slide. And it will ask you, okay, what's your range of t values? Now, when we graph this function, which I'm going to zoom in on, when we graph this function, Our domain restriction, or restriction on the t's, was negative pi over 2. And if you're wondering how to type pi, just type the letter pi over 2. And if you notice, we're getting the same chunk of the parabola that we saw before. I'm going to change the settings of this so that it is red and dashed, because I'm about to show you something pretty cool. You can also illustrate the orientation of the curve in real time. And the way to do that is to type another ordered pair, but this time put some unused variable like c, f of c, and g of c, and then add a slider. A slider is just a value. It's just like a variable that assumes a value, and you can move it left and right. For example, right now it thinks c is 3.6, but I can define this to be from negative pi over 2 to pi over 2, just like it was in our graph. Hold on. And I'm going to do one more thing. I'm just going to have this go one time from, what's this do? Stop, spoiled it. Okay, dagnabbit, everything just totally got undid. Let me fix all that. Okay, so we'll back this up. All right, so what I'm going to do is I'm going to animate this. I've typed this ordered pair. I could label it if I wanted to. It's going to keep track of the ordered pair, but I don't want to. And I'm telling it, all right, I want this slider, this C, to start at negative pi over 2, end at pi over 2, and let's animate it. And so there's the orientation. Now, when we did this one, I also mentioned that if we let the parameter go longer, then it was eventually going to go back up. So what I'm going to do on this one is I'm just going to tell the parameter to go all the way back to, we'll say negative 20 to positive 20, and we'll start it back at the beginning. Whoa. And it's going pretty fast. Kind of hard to see it, so I'm going to tell it to slow down. That should be good. And if you'll notice, what you're witnessing is the location of this point as time moves forward, and it's going back and forth just like we said it would. I've got it set to only go through one time, so when it reaches the end, it's going to stop. Of course, we could stop it and slide it manually if we wanted to. And there's where t is equal to 20. And if you have this set up, then you can easily graph any parametric equation by simply changing your functions. For example, let's do the first one, cosine of t and sine of t, which should be a unit circle. It's acting persnickety. Hold on. All right, cosine of t, sine of t. And remember that when we drew the graph, we put some artificial limitations on it. Anytime you sketch a graph in Desmos, it has to have a range of t values. If you don't want it to have a range, then just put some really large negative and positive numbers, like negative 100 and 100, and it'll pick up most of the graph that you'll be able to see. Of course, there are exceptions to that. And let's start this slider at 0, and let's just run it up through 20 and see what happens. Well, there's a big surprise. It's just going around the circle. Almost as if the parameter were measuring the angle it was making. Oh, wait, because it was. Let's stop that animation, please. Thank you. And let's pick another pair of equations, parametric equations. Let's do the second one. X equals t squared minus 2t and y equals t plus 1. X equals t squared minus 2t. And by the way, if you fiddle around with these, as I just did here, you can create some really messed up graphs. I challenge you to see how weird you can make a graph. I will be able to make weirder ones than you. Trust me, I've had more experience. And g is equal to t plus 1. We have our parabola as expected. But the reason I wanted to do this one wasn't to animate it, because somewhere around here there will be an ordered pair. There it is, and it's going to shoot off. We'll have to zoom out to keep track of it, but it's almost like an orbit whipping around the sun, a comet whipping around a sun, and then going off on its merry way. By the way, there is a lot of parabolic motion in space, so for those of you going in that direction, That would be Calculus 3. Get ready to see some. But the reason I wanted to do this one was to show you that we can also confirm that our rectangular equation is correct. Recall that the rectangular equation that we got for this pair of parametric equations was x equals y squared minus 4y plus 3. Well, let's just go into Desmos and ask it to graph that by adding a new equation. X equals y squared minus 4y plus 3. And we'll make it a different color just so it stands out a little bit. Make it green. And we can turn it on and off to see that that rectangular equations graph does coincide with the parametric curve for these parametric equations. All right, I'm going to wrap up this video by taking a look at the one equation we haven't yet, which was the middle one, x equals tangent of t and y equals cotangent of t. We already determined in a previous video that its rectangular equation was y equals 1 of x, since cotangent is 1 over tangent. And I kind of roughly sketched that graph, but I really wonder if there's any domain or range issues created by tangent and cotangent, because both tangent and cotangent have asymptotes on their graphs. So let's take a look at it. All we have to do is go back up here and change our functions to tangent of t. Whoa. That's trippy. It's amazing the things you'll accidentally stumble upon as you're typing these. Tangent of t. And cotangent of t. T, please. Let's go to the zoom default zoom level. And yep, gives us y equals 1 over x. So, yep, sits right on top of it. Now, I am kind of curious what will happen to the point as we animate it, because when we start at 0, cotangent is undefined. So watch the point. Let's see where it goes. Oh, it almost like it teleported. Let me slow it down some. Crazy. That's just because it's jumping over the asymptotes for tangent and cotangent when it leaps from branch to branch. All right, so I just wanted to share Desmos with you, and I strongly recommend using it to help you understand the concepts in this section and to get some graphs sketched. And you can even use it outside of the section.